It was really tough. Then they start at midnight my time zone back in Seattle. So yeah, I'm Jeffrey Early, and this is work done with Gerardo, Leslie, and Pascal along, and Pascal will actually be presenting shortly after me.
I'm sorry, just give me a minute.
Sure. That works.
Sorry,
okay, so this is forward. Okay. Okay, cool. So what I'm going to do is do a quick overview of the wave vortex decomposition, which I spoke about last time, and give updates on what we've done since then, which includes converting the decomposition into a model. And then I'm going to spend sort of the last half of the talk talking about when the decomposition fails and how to assess this in terms of APV and APE. So, all right, so as a quick overview of our wave vortex decomposition. So the idea is, okay, you start with a nonlinear set of equations of motion, and these are more simplified than what a lot of other people are doing, but this is non-hydrostatic, rotating, Boussinesque. Sort of the key innovation here is this is variable stratification, but we're still limited to flat bottom and rigid lid, although we've relaxed the rigid lid condition recently. So then you want to go solve this equation. So you turn all those total derivatives into partial derivatives, and now you got a linear set of equations. You can then go write down all of the solutions for. So as is in all of these talks, right, that your primary two solutions are geostrophic and wave solutions. In the way I've written these here, we have for each wave number, K and L, you have a set of vertical eigenmodes represented by F and G. So the geostrophic solutions are just geostrophic balance. And then the wave solutions, those eigenmodes depend on wave number themselves. And of course, they have a more complicated phase propagation. And there are two positive and negative rotating wave solutions. And then there's a few special case solutions that depend on usually if you're in K equals 0 or J equals 0 cases like the inertial oscillations. Okay, so then one of the key things is that all physically realizable states of this system I presented in that first slide are the sum of these solutions. It's a complete basis. And so you can represent any U, V, W, and I'm using eta here as a equivalent to buoyancy anomaly and pressure, okay? So then you can just decompose, do this in reverse and say, go invert everything and say, okay, so if I have some U, V, and buoyancy anomaly in my fluid, what are the waves and vortices? And so what we've done since last year was there's a nice set of code now for just doing this, where you can initialize a particular set of stratification, input your U, V, and eta, and it projects everything onto these wave vortex coefficients. Now you do this for each instant in time, right? This is not time filtering. This is just, you can think of it as PV inversion and then phase unscrambling. But beyond being a complete basis, the key feature that's really useful is that it's energetically orthogonal. So each one of those solutions is energetically independent from another. So the depth integrated total energy of your fluid is actually the sum of the squares of those components, which is what's cool. So this is basically like a Parsifal's theorem, but for wave vortex energy. And entropy is also orthogonal here. So more recently, what we've done, by the time you're computing using these to compute fluxes, energy fluxes between these different wave vortex modes, you're basically running a model. So you may as well run a model. So this is then so what we've done is made a spectral model where instead of the basis being sines, cosines, and Chebyshev polynomials or what have you, the basis is these wave and vortex solutions. And so the nice thing about this is that each degree of freedom in the model has a dynamical interpretation. And so the only thing that nonlinear terms are doing is reshuffling energy. And then every transfer mechanism you can relate back to some physical interpretation. And as it turns out, you gain a lot of computational efficiency when your stratification further away it gets from non-constant stratification, because this modal projection is very efficient. So for a project with Barbara Zemskova, we set up in the wave vortex model a study done by Aslan and Young just a few years ago, where they spun up a turbulent geostrophic field in a semi-realistic stratification. They put in inertial oscillations at the surface. And in their study, what they did is they time-stepped the model forward with a modified Young and Benjalul model, which is a reduced dynamics. So it's basically a QG model coupled with a near inertial oscillations and propagate through there. So we repeated that same experiment, but in this model is, of course, full Buzan-esque, but it's decomposable into these constituent parts. So I guess I'll just start playing this and see if it'll go. Okay, so on the left, you have the geostrophic vorticity field, and in the middle, you have the internal gravity wave vorticity, which started out as none because there was no internal gravity waves in here. And then you can watch as they start to take the shape of the geostrophic field, and then in the far right panel, you can actually see the internal gravity wave spectrum plotted in vertical mode and wavelength space. And again, key here is there's no time filtering. So in fact, you can see fast motion still occurring in that geostrophic field that they're separated just by PV. I'm not going to spend too long talking about this. I want to get to the second part of the talk, but the story here is pretty simple. As it turns out, it's really cool. Geostrophic energy basically stays constant, and all of the inertial energy gets converted. Well, not all of it, but like all of the internal gravity wave energy comes from the inertial oscillations. And then with the model, we can actually go and track exactly which fluxes are causing this. And so ends up being a very simple story. And I'm happy to talk about this more later, but basically it's the advection, inertial oscillations advecting across that geostrophic vorticity field is the only flux term that's moving energy between the fields in this case. And in fact, in the geostrophic field, you see there's just, it's just involved in the triad interaction, but it's not actually changing energy. Okay, so what I wanted to get to was talking about when the decomposition actually fails. So the whole decomposition hinges on QGBV, which is of course not conserved in the equations of motion, but it's a pretty good approximation in several regimes. And so one of the things we want to have a set of conserved quantities from the linear equations of motion that coincide with the linearized conserved quantities from the nonlinear equations of motion. And when we first published this paper 2 years ago, we didn't know how to do that. I'll get into this in a sec. And as part of this, how we got here too was we actually extended this methodology to the free surface and had to go back and sort of reevaluate how to compute some of these conserved quantities. So the answer and the way to do this, it turns out, is to write the equations of motion in terms of isopycnal deviation instead of density perturbation, which has of course been done for many, many years. But the conservation equations turn out to take a really nice form. So the idea is you have a no motion state. That's what I'm calling rho no motion. That's there's no motion in the fluid. Everything's adiabatically rearranged in a monotonically increasing density function as you go deeper. And so then in your classic way of writing this, you would write rho total is the sum of that rho no motion plus what I wrote as rho excess. That's your excess density. But alternatively, you could write this as isopycnal deviation, which is to say, okay, if I have some particle up here, how far would it have to move up or down to have gone to that no motion depth where it should be. And so instead of using rho E everywhere, you're now using this eta. So it's rho of no motion Z minus eta, which is just that deviation term. And so your conservation laws switch from d rho dt equals 0 to d dt of Z minus eta equals 0. Right. So here's what goes wrong using the excess density formulation of the equations. So the linear equations of motion give us QGPV at the lowest order, right? But so you take Ertel PV by just plugging in rho total, then it at lowest order it ends up neglecting the vertical advection of the background density gradient. And so you can't recover QGPV just by naively expanding that. So this is a problem if you want to assess how good this decomposition is doing, because I can't compare it to the correct answer, right? I have my approximated answer, but I don't have a full answer. So Wagner and Young in 2015 have this form of APV where they try to solve this problem, and this does work, but you end up with this perturbation expansion that is trickier than it looks in the paper to actually go expand. And so it's fine, it helps, but it's not an exact closed solution. Well, it turns out all you have to do is use Z minus eta as your conserved quantity in your PV conservation law, and then you end up with this super simple 4-term APV conservation. Now, the eta in here is a little different than the eta in QGPV. This is the QGPV eta is a sort of an approximated poor man's version, and this is the true isopycnal deviation of each particle. But regardless, you can compute it, no problem. And so this was actually noted in '95 in the paper by Peter Mueller, but he unfortunately said that it didn't apply when there were isopycnal overturns, which isn't true. It actually is just as generic as the excess density formulation. So then, so as part of this, yeah, so if you want to get a conserved potential energy, you can go use the result from Holliday and McIntyre, where they actually is already written in these same isopycnal deviation coordinates. And so then that system is closed. For our purposes, we were extending this to the free surface. We went and revisited that methodology. And it turns out there's also a really nice, basically one-line way to get the APV conservation from Holliday and McIntyre. And that is, if your potential energy is just rho GZ, then just go ahead and write that in terms of your materially conserved quantity of, instead of using a Z, use a Z minus eta. So then you get material conservation. That's the top line. Just rearrange that, and you're basically done. You get an APV conservation that gives you the correct buoyancy flux term on the right-hand side. Now, if you want to go to the perturbation equations, which is relevant for the rigid lid case, then you need to go ahead and remove the hydrostatic pressure. And then you end up with what's exactly in Holliday and McIntyre. Okay, so the upshot of this and the conclusion of this is that we now have a set of equations written in this isopycnal deviation coordinates that are fully conserved. All the conservation quantities can be exactly computed. And so then we can go and we can compute them and compare to our linear conservation laws and see how well our decomposition is doing. So we expect things to fail when there's, high Rossby number, high Froude number, things like this. And so we're starting to go investigate. We've been looking at where this decomposition fails, and this is where we're actively looking some of the research. And that's it. So then my conclusions are basically, we have this wave vortex decomposition, which is now, the tools are more robust, and I'm happy to share. They're online. I haven't really advertised them, but it's all available. And then there's even the model, if you want to actually go run that too, that will compute all this for you. And then I think we now have a way of assessing how good this is all working. So that's it.